And to Imoto and the folks that just did the previous seminar. Right now we have a seminar about avoiding electrical pitfalls. And I'd like to introduce Dave Beecher from Fast Pinball. And at the end of his presentation, if you have any questions and he opens the floor for questions, please just stand up and go over to this microphone in the front and address your questions from the microphone. Okay, kind of free form. Enjoy the festival. Dave Beecher, it's all yours.
All right, thank you everybody for coming. This is one of my first times doing a solo event up here, so we'll see how this goes. And new material. He's in the booth manning it, so anyway. So to get started, so we're here talking about avoiding electrical pitfalls. So this is an accumulation of all of the developers out there and all the crazy things we've seen over the years and all that. So, you know, it's so nice. We have over 150 people now on our Slack group that are building all of their pinball machines, and it's so great that some of the senior people now help all of the newbies coming in and all that kind of stuff. So I am down to probably 3 tough questions a month. So I actually appreciate getting those, and anyway, let's get started. So I am the one at FAST that does all the hardware and the low-level firmware. So to date, we're over 70 boards. We counted that up last year, so definitely keeps me busy. I have done this my whole life, but never working on this many games and things like that. So I love what I do with all the pinball stuff. So Fast Pinball has 2 basic systems. We have the retro boards that are the System 11, System 89, and System 95. These are for the 2.0 kits, and soon we'll be letting you have these as replacement boards to completely swap out, you know, these boards in your machine to play the original code, but then you also have the advantage of being able to go in and start taking control of the assets and doing what you want with the machine. So if you want to make your own version of a 2.0 or whatever you want, that's what the retro systems are all about, or the retro platforms. So the one we're talking about today that's used for the homebrew and machines that go into production is the Fast Modern platform based on our Neuron. The Neuron is the controller that's at the bottom right over there, and you can see all these cables that come out to go to all the I/O boards. And then what we introduced this year also is these expansion boards that can do lighting and some other things like that. So digging right in, it all comes down to power supplies. That's where it starts. From the line cord in, we get the power supplies. Fast needs 2 different power supplies to run. We have a 48-volt power supply that runs all the coils, you know, everything high current comes from the 48 volts. Then we have a 12-volt supply that pretty much runs everything else, the controller, the node boards, shaker motor, you know, the LED lighting, all of that. On our first product, the Nano, we had 5 volts going to that controller, so we had another supply we required. And 5 volts in the system, especially when you go far distances, we were noticing with lots of LEDs, big loads, that it was just too big of a drop. So we would have LEDs changing states, colors starting to go out, all that kind of stuff. So when we introduced the Neuron and went more into commercial machines, we decided to do DC to DC converters everywhere for 5 volts. So now we only require 2 power supplies, 48 and 12. So in Homebrew, if you were to sit there and develop your own system or start trying to piece together your own components, power supplies are pretty critical. So I'm going to talk a little bit about what you're looking for. The biggest issue with power supplies is what happens when they overcurrent. Because when you hit those flippers, when that magnet turns on, any high current loads, almost every power supply overcurrents. So there's this one mode that power supplies do. They either shut down or they go into what's called hiccup mode. So hiccup mode is where a power supply is overcurrented, and for 2.5 seconds, it turns the power off. Well, that's not very much fun when you're playing pinball. You hit the flipper and you don't get it again for another 2.5 seconds. So for the 48-volt power supplies, what you're really looking for is something called constant current, so that when the power supply overcurrents, rather than just shutting down or doing something different, you just want the voltage to start going down and then come right back up. So you can kind of see right under input right there, it's the, you see protection. Sorry, it's under protection, overload, protection type, constant current limiting. So on your 48 volt supply, that's important. On the 12 volt supply, it doesn't really matter. You can choose if you want it to completely turn off at overcurrents or just, shuts down for 2.5 seconds. Typically on the 12 volts, that's not an issue. The line power wiring is pretty simple. You have an AC line in on the right that you can see it there, some type of fuse, switch, and your 48 and 12 volt power supplies. One of the most important things here is to note, the line fuse. The inrush currents of these power supplies are pretty significant. You can follow some things online, but yeah, if you put too weak a fuse in there, repeated hits will eventually make it go. So it's very critical to make sure that sized correctly. So here's some of the pitfalls shared with the FAST community. So the power supply, unfortunately, you can't do very much until you start putting your components together, and the power supply being the first is usually getting the worst crimps. Well, that's not really good because it's also the crimps that also have the high voltage on them than everything else. So you might practice a few times on crimping, go to the website. We have some, on our website, I'll go there very quickly so you can kind of see this. We actually have, no, it's not working. We actually have topics on there on how to crimp wires properly, what tools to use and all that. So almost all this information I'm showing you is on the website, but we're mostly here to talk about the pitfalls. So one thing to do, obviously, is pull on them, do everything you can to make sure that they are not going to come out. We've had a few people where the 110 volt came out and touched the case of the power supply, for instance. That doesn't really end well. So avoid using unstable power supplies like the ones you would use for PCs. A lot of times, PC power supplies were desired because they're so inexpensive, but at the same time, they have so many outputs, and you're only going to be using one or two. If you were using 5 volts for LEDs and 12 volts to run our system, there's a whole bunch of unused power out there, and a lot of the PC power supplies like to have all those loaded, otherwise they're not as stable as you'd like them to be. So if all of a sudden your 12 volts goes, berserk, starts damaging stuff, anyway, don't do it. We've had a lot of problems with that. Be wary of supplies that have incredibly high current. We've had a few people in our group that found some really low cost on 50 amp power supplies. It's awesome that you can weld with a 5 volts, but at the same time, it doesn't really belong much in a pinball machine because all the cost you save is going to be made up for with that 8-gauge wire, fuse blocks, and everything else that's starting to look like an RV or a boat rather than a pinball machine. But if it looks cool, you can probably still go for it. Just know what you're doing. Choose power supplies capable of managing the pinball overloads. We talked about that. And then obviously wire gauge and some other things like that with wiring errors. So all of this stuff you can find on the website on what the best approach for all that is. So the power supplies then go into a filter board, and the main objective of the filter board is these 3 large caps that you see on the bottom there. There's about 30,000 microfarads of capacitance. When you hit your flippers, each flipper takes about somewhere between 6 to 12 amps for somewhere between 14 and 30 milliseconds. So that's going to overload almost any power supply you have on the machine, especially if multiple go off at the same time. So those capacitors are where all of your power comes from to run those high current loads. And then you can also see on this board that we go out to all the different power supplies for all the different sections of the machine, the neuron, the back box, topper, Essentially, this is a board that combines the power supplies with the filter caps and then goes out to feed everything else in the system. So we stabilize the 48 volts for the flippers. We have an auto 48 volt cutoff when the coin door opens. All of these outputs are fused to get in the system, and you can kind of do the rest there. So some of the pitfalls with the FAST community, we really don't have too many problems with this board, but oddly enough, the biggest one is the one that everyone gets so excited they forget to hook up the coin door, the switch in the coin door that disables the 48 volts. So when you're trying to get your thing going, and that happened to you? Okay, all right. So anyway, incorrect wiring, so that comes up quite a bit. Getting the 48 mixed up with the 12, that usually doesn't end well. It doesn't happen very often. An appropriate wire gauge, that typically happened with the 50 amp power supplies and some of those type things. And choosing inappropriate fuse ratings, as long as they're too small, okay, too big, better figure out what's going on there. So here's how FAST tries to help with all this. We have some really good documentation online. We recommend some power supplies if you choose to do them. We also came up with a standard for all of our wires so that if anyone in the homebrew community looks at someone else's machine and they happen to follow those color schemes, it's like everyone can actually kind of figure out what's going on. Actually gives some good help. And we supply some wiring diagrams, and we try to design the hardware to streamline all the wiring. And what we mean here is that almost every single terminal in the fast system is labeled. You know, if it's 12 volts, it says it's 12 volts. If it's ground, it says it's ground. So when you're wiring and crimping and doing all that stuff, you just can look at the boards themselves and see what's supposed to be happening there. Powering up the system once you get the filter board is pretty simple. We only require one power supply coming in on the fast neuron board over that. From everything else is just RJ45s to power up all the rest of the node boards in the system. These are the boards that will be running your coils and switches. So overall, just Cat5, that's it. So the one power supply line comes in just to the neuron, and that powers up the rest of those boards. So here's a little blast from the past. We're looking at the switch matrices. We do not at Fast use a switch matrix because you have rows and columns. The old machines all had an 8x8. You save a bunch of I/O, but at the same time, your wires are kind of a mess. You almost need to make a wire harness because the switches are everywhere. And also, when you have a switch matrix, there's this ULN 2803 on the right. This part is treated like a fuse. There's no way to protect output drivers on these things when coming into contact with 48 volts. That chip gets destroyed. So because of this, we wanted to have everything direct input into Fast. And this way, especially with home brewers and all that, they're not going to run into the problems of having this fuse chip blow out in their boards. However, I had to do it. On all those retros, this is the way they did it. So to keep with the tradition of the replaceable fuse, I use surface mount, as you can see on the right-hand side, but I also have a dip part right there. So when you do blow it out, you can socket that thing, and now you've got your fuse chip. There you go. So anyway, here's the way the fast switches are wired in. The one thing I will point out here is that our switch ground, that purple line you see here, it goes on that. This is very important that this never goes anywhere else. We have what we call toxic ground to make sure the coil grounds never come in contact with the switch grounds. To make sure our switches are quiet, our boards actually float a little bit. Those switches float with the board. If you sit there trying to start contaminating from getting grounds from other spots, it may not end very well. So here's some of the features that the fast system does for the switches. We have really good protection against ESD and high voltage. We, again, simplified its direct connect. We have, all kinds of, we supply current into the switches so that almost any switch type you have, it'll work, like infrared switches direct, Hall effect sensors, anyway. I won't sit there and bore you going through all the details on this. You can look at that later. Okay, so here's some pitfalls about switches from the fast community. Grounding issues I already talked about. Sensors that emit voltages instead of like grounding stuff out. The inductive sensor over on the right puts out a 12 volt when it sees a ball in there. So since we are looking for a ground, putting 12 volts out is not going to be seen. Also, contacts that have tungsten contacts or switches with tungsten contacts. Tungsten will corrode if it doesn't have high current going through it. So many people have used the same switches that came with their pinball machines that would directly drive all of the flippers, and over time these corrode, and all of a sudden the digital signals don't get through. So anyway, tungsten switches, don't use them. Switches are not always switches when it comes to digital stuff. How to help everyone wire all the switches in, great documentation, and some killer hardware to make it really simple. So drivers in the past, this is out of a schematic. I believe this one was from, was it Diner? Anyway, what I really liked about the past is that the forefathers of all this, they had a digital driver coming into a transistor driver, yet driving another power transistor. And if anyone's ever repaired these boards, you'll always notice that almost 90+% of the time, it's only the tip 122 or tip 36 that burns out. So they drove this very hard that one tip 122 or 36 is never running in its linear range, so it dies gracefully. And even if that one does go out, sometimes that 2N4401 just to the left of it might go out, but almost never do you get into the digital side. I really like this, and I try to keep this tradition the same with fast. So if you look at any of our boards, our drivers, our high current drivers are over there on the right, just by the connector as it goes out. And then you see we have our second tier, our MOSFET gate drivers, and then we have a blanking circuit, but right beneath that, you can also see the digital stuff that drives it. So we actually still have those same 3 layers. So as home brewers, you're gonna sit there, and it's almost like the badge of honor when you burn up your first MOSFET. You're gonna do something. You're gonna put the diode in backwards. You're gonna have a short. It's gonna happen. But at the same time, when it does happen, almost like 90+% of the time, just like the original Williams games, is like it only takes out either the MOSFET or the TVS that's out there. So it's kind of an easy repair. MOSFET versus transistors, just kind of general information here. It's, voltage-based versus current-based, and, MOSFET's much better. Transistors a little worse. They worked for years, brought us lots of joy, so. When things go wrong. So overheating is the big one, and it's funny because everyone thinks like overheating means when you touch the part it's hot. Not that case in MOSFETs. MOS have what's called an SOA, safe operating area. If you keep putting more current through it, running in a linear range, it's a matter of time when it's gonna go out. It may have never got hot, but that doesn't mean you're not damaging it. So we try very hard to always keep the MOSFETs in their safe operating area. They don't like over voltage at all. If you get, I've tested all the MOSFETs we use, they die right at 108 volts, and you would think, oh my gosh, that will never happen. How do you ever get to 108 volts? Well, when you don't have that protection diode on there, and the field is collapsing in those coils, especially magnets, the voltage does get up that high, it causes a lot of heat, and if anyone from the fast groups ever played with magnets and done some bad things, they'll probably notice that occasionally they take out a MOSFET. So I think you guys can just read the rest of that, it's fine. So pitfalls from the fast community: incorrect flyback diode installation, putting that diode in backwards, omission of the diode, inadequate PWM protection for high current magnets. So sometimes a diode doesn't quite cut it. A magnet almost makes a better DC to DC or power supply converter within the machine itself. So sometimes that might require a snubber, and you can find more information about that on the website if you ever run into that. So here's an image someone shared. So this is what a driver looks like when it burnt out. I don't know whether this was a magnet or what happened there, but you can kind of see that one D6 over in the lower right corner, maybe left corner for you. Anyway, that TVS kind of opened up, shorted out, and you can see the burn marks on the MOSFET. But again, it was an easy change. You just swap that MOSFET out, this board's probably gonna be right back in service. So, coils. So, there's a lot of people will take an existing machine that had like 28 volt coils and then try to put a 48 volt power supply in there, like an older machine, redo one, that's their starting point. Well, when you have the incorrect voltage on the coils, it's like you're either going to, if it's a lower voltage, you're putting a lot more stress on the power supply and components, and if it was a higher voltage coil, then you're probably not gonna sit there and get the power that you wanted. And so trying to gauge all your coils correctly is one of the big pitfalls that you run into. Not having the right coils will sit there and not give you the result that you want. So here's a question. So of these 3 coils, how many people think that the one on the very left is a drop target reset, the one in the middle is a magnet, and the one on the right is a flipper coil? So show of hands, how many people think that the target reset is the one that's going to be the most damaging to a machine? How about the magnet? What about a flipper? Nice. So yeah, most people got it right. It's actually the magnet. And the reason is a magnet, because of all the metal around it, the flux field on the magnet is so much more, so that when it releases energy, if there's no diode in there, it's trying to take something out. It will. So the flippers they're almost the same impedance in many cases. The flipper has the same amount of ohms as that magnet does. Also, the magnets are driven a little harder in certain games. So anyway, it all adds up to, I don't like magnets. Every time someone's got a magnet, it's like, okay, use a snubber or make sure that diode's in the right spot. So here's some of our documentation kind of showing, how easy it is to hook up coils. We are very specific. Hey, look at those diodes in there. Try to make this as clear as possible, because when this stuff goes wrong, you start losing some hardware or not having a good day. And I just throw this in here too. If anyone's never heard of a snubber or seen a snubber, these are something that we're doing on some of our boards. So if you do have a load that's very problematic, you're running your magnets really hard, we make this kind of very simple snubber board you can put on your electromagnet to make it better. So this is what it looks like. Does anyone know this game? Adams, yeah, Adams Family. So Adams Family, it was very common for Adams Family. They didn't have fusing low enough to, when the magnets would take out the transistors, and almost all transistors and MOSFET short on, it would just sit there and cook all day. So that's the number it did on this particular Adams Family when it got stuck on. Fuses, boy, this is, I never had any idea. I've used them all throughout my career. I never had an idea how bad they are. They are actually time delay devices. So you can kind of see the charts here. This is all for a 3-amp fuse. We have a fast blow, a normal blow, and a slow blow. So they're not that far apart. They kind of do all similar things. But really, let's look at the numbers for a second. So if you have a 3-amp fuse and you got 3 amps in there, it could take 10,000 seconds to blow if it's going to blow at all. Because of the margins of the fuse, it may never blow. But 3.5 amps, we're at 100 seconds for fast, 200 seconds for a normal, and 400 seconds for a slow blow. Well, look at how, as time goes on, you can see that, man, a fuse isn't really protecting very well. And you can have 12 amps going through it, and you're still running at a slow blow. You still got 1 second at 12 amps going through that thing. So even though for long-term effects, they will do some things, like in the short term, they may not always protect. And here's the big thing that I can't stress enough. In the past, we had that big chunk of transformer in there, and it's like when you overcurrented it, it could put it out. It would just keep putting out voltage to try to blow that fuse. With all these nice switching power supplies we have and all that, when they say they put out 6 amps, they put out 6 amps. So if you have a fuse at 6 amps and you have a power supply in a nice new power supply and put out 6 amps, it's never going to blow that fuse. Even at 5 amps, it might not blow it. So my recommendation on this one, fuses are cheap. Go get a whole kit on Amazon. Just keep going through them until you get the result you want. Make sure that when something goes bad, that fuse will actually open up. And another thing, I knew, but I didn't know the actual numbers. A lot of manufacturers of fuses won't tell you this. But at the very bottom there, you see in these specs, there's something known as thermal shock and life. So if you keep stressing the fuse out temperature-wise by keep running through, you only get 100 cycles in that. I don't know how many times the flipper is pushed in there, but if, you know, in one setting, but I'm pretty sure it's way over 100 cycles. So if you fuse that in appropriately, you're sitting there pounding on that door, bending that metal inside that fuse to the point of fatigue, and it can open up. And then you'll see the life also, they're only estimating at the 80% rated current, which is going over current all the time on flippers. So if you ever get that random fuse that blew and you don't know why, it's probably through this fatigue. And maybe up it or try to find a solution that will solve that. So here's the tools required to wire a pinball machine. So obviously a lot of tools are required, 3D printers, cutters, all kinds of other crazy stuff when you're building the machine, but on the electrical side it's actually pretty simple. We need a wire cutter, a stripper, a crimper. A soldering iron doesn't have to be good for just putting the wires on the coils, but doing some rework on boards, you probably want something else. I got a lot of pushback on the screwdrivers because it's like when you see the numbers on the next page here, I guess one more page. So I'm emphasizing good tools here, and here's the why. Check out these numbers. You're going to cut 1,581 wires. You're going to strip 1,581 wires. You're going to crimp about 1,400 times. You're going to solder 167 times, and you're going to run the screwdriver 14 times. Now, Aaron, my business partner, gave me crap because he goes, you use a screwdriver way more than that. Okay, look, it's just on the power supplies. We don't use screw terminals for anything else. For electrical, just electrical, not mounting stuff, it's 14 times. So this is assuming 64 switches, 200 RGB LEDs, and 16 coils. Now, if you want to get that down, you can buy, pre-crimped wires for the LEDs and your play fields and all this kind of stuff. But the nice thing is, if you crimp 1,400 times on a pinball machine, if you weren't an expert by the time you started, you will be by the time you stop. There you go, true. This is assuming. Typically, is that for average pinball machine or just customs? Pretty much when you go start manufacturing games, you will be doing wire harnesses ahead of time and things like that. So it's mostly just plugging cables in at that point in time. So here's some crimps. You can probably see a couple that don't look too good. There's actually one of them up there that's supposed to be the good one, which is on the very right. But from the homebrew community, this one got me. This one got me good. That one on the very left that you see there, what happened there is somebody forgot to strip the wire and just crimped it. So this is not the same one. This is we remade them to demonstrate it. But you'll see that there's no wire underneath the crimp where you see the first crimp right below the contacts. You'll see there's no wire in there. Anyway, it looked perfect, and I kept looking at it, looking at it. There's no power going anywhere, and that's what it happened to be. So strip your wire before you put it in the crimp. Yeah, the right one was good. Now, the right one, it's like theoretically, the pin, that part moves, the clip kind of moves in when it comes in. So if that wire was a little bit longer, it would start scraping in a spot that you don't want it to scrape. So if it should be a little shorter on that. Don't have, not a lot of slot past it, but yeah, the middle one definitely. And someone just recently did that, and because there was so much material at the top, it shorted and caused an issue. So how we've helped here is we try to provide some wire gauge recommendations on the site. We tell you what wire types to use. Anyway, there's a lot of stuff on the site about wiring, so I won't bore you with all the details. You can just look at the site for that. So here's what we try to do to keep everything consistent and allow all of, when we're helping or the community's helping, if you follow these wire things, everyone knows what's going on in your machine. So this is the 18 gauge wire. This is what we use for all of the high current stuff. We kind of tell you on every single pin not to exceed 7 amps. And so we have red for 5 volts, yellow for 12, blue for 48, and black for ground. And then some control lines can be white or gray. And then when we come to our low voltage wiring, you kind of see there's all of our colors for that. And then on our AC line cord, that's going to kind of vary a little bit by country, but at the same time, we're trying to use the standard colors. We did have one person use all black when they were doing their AC wiring, and they accidentally got ground and hot mixed, and again, didn't end well. So here's a little bit more just on some of the documentation. I won't get into that. Okay, so pitfalls were shared with the FAST community here in wiring. So insufficient service loop. So what this means is when you go to lift up your playfield for the first time and you didn't leave enough wire for it to lift up, it's a bad time to find that out. So I recommend putting some service loops in there, meaning you kind of tested to make sure your wires were long enough the first time you lift that up. That's, God. Oh no, okay. Faulty crimps, so especially in the beginning, don't trust your crimps. Weak solder joints, you'll get good over time. Anyway, confusing color schemes. My favorite is, I think it was Chris. Sorry, Chris, I'm not trying to offend you here. But anyway, every wire in his pinball machine was orange. He asked me to try to help him at one of the shows, and I felt so bad for him, I actually helped him rewire his machine during the show. So here's a couple of things when wires go wrong. The one on the right there from Mike, this is when he discovered that all of his wires were too short. You may be able to see all the crimp butt joints right near that connector, so he had to extend all of his wires to get his playfield to lift up. And then on the image on the left, this just recently happened. It was just a bad crimp, and you can see around that fuse on the left-hand side, the 12-volt supply line came off, and that's the 48-volt fuse, and it's on the side of the fuse that's not even fused. It's the raw 48-volt coming in, so it combined 48 and 12. It obviously gave a little bit of an arc show there, and anyway, he didn't see it, so it went through 2 controller boards, but he was nice enough to give me the photo to share in his misfortune, so thanks for that, Ben. So this is a little bit advanced topic, but it's also something that a lot of people run into. We started to call one of our grounds toxic ground. So everything on our 48-volt power supply and anything running coils and all that, we have this thing called toxic ground. Now, what does that really mean? Like, is ground ground? It's like, yes, but there's a digital ground, there's an earth ground, there's And these can all be at different levels, even though at some point they're probably all tied together, but resistors are wires, and so it allows variance to be in there. Well, 12 volts, especially on a flipper, is just absolutely ridiculous. So I have the simulation down here, like where R5 is there. You can see where it says coil simulation circuit. I have a 2 ohm. Now, a lot of flippers are 4 ohm, but if you fire 2 of them off at the same time, now you're down to 2 ohm. So this is a traditional driver, and you'll see it on the next thing when I'm pulsing it. This is wired correctly, so you can kind of see down at the bottom I have toxic ground, and it's coming all the way up to where my power supplies are, where V1 and V2 are. So you see there's a chunk of wire, R2 is my wire, but this is wired correctly. The 5 volts we're trying to protect on the other side comes all the way up to a common ground. So what I expect to have happen is that when the coil fires, we're seeing about, so that top of that green right there, that's 1.5 volts. So what happened is that the ground that is sitting there by toxic ground rose by 1.2 volts because of the resistance in that wiring. So you can kind of see the red line down below. You don't ever see it move. The red is actually my 5 volt ground. It's sitting there going all the way up through the wire, so it's safe. It did not see that 2 volts. But let's look if someone did something a little different now. So here's the circuit where we have the toxic ground is actually tied into the same line coming out of the playfield as the 5 volt ground. So now what's going to happen is all that R6 path, that wire right there, is going to sit there and dip, higher when the coil shorts out. So what really is happening is 48 volts is coming down and ground is coming up. And they both come up in worst case that I've seen about 2 volts. So let's take a look at what this looks like. So now what just happened is this is looking at 5 volts and ground. So the 5 volts stayed constant because it's not tied to that ground in any way. But this is now, we came up to that same 1.5 volts in the 5 volt power supply. So if you take 5 and you minus 1.5 volts, if that's coming into your LEDs, your processors, all this other kind of stuff, not a real good scenario. So anyway, follow the guides, make sure that the grounds from the coils and the grounds from everything else that's delicate do not get combined anywhere else. They're supposed to be combined at the filter board only, and it'll save you a lot of time. I mean, this is what blows LEDs out. This is what blows out your 5 volt stuff. You have no idea why. Just at the last show, someone burned out one of our controllers that still ran on 5 volts for the exact same thing. We followed down. It's like, okay, there's a toxic ground and your 5 volt ground tied together. That's what happens. So another common thing when you're running a whole bunch of LED chains, it's like I just ran the math for this yesterday. If we have 32 LEDs, these are RGB LEDs that are coming off that controller board right there. If you have 32 of those, you have the wire, this is 22 gauge wire, you have the wire length, and you also have all the connectors in and out of each one of those things. So for 32 LEDs, you're gonna have 64 connections, and you're going to have a length of wire. So in my example, I used 5 feet. So I'm going to say, wherever all these LEDs went on the field, I have 5 feet. Now, 5 feet really means 10 feet because there's 2 wires to a circuit. You have ground and you also have 5 volts. So doing the math on what the resistance is on the wire plus the connections, at 10 milliamps per LED, that's already a 0.6 volt drop by the end. So what happens is you start getting, the blue LED requires the most amount of power in all of these RGB LEDs. So the blue is going to start cutting out like right away. So what do you do about things like that? Well, it's like, you don't want to go to thicker wire because it's going to be more difficult to do. So what you can do is just put power either in the middle somewhere or back at the end. So you're putting power at the beginning of the chain from the board, and now you're putting it at the end of the chain as well, and possibly in the middle. And so what you're doing is almost like little substations out there repowering all your LEDs so you don't run into problems there. Typically the question is what kind of problems do you find with that? So, the blue is going to go, the green is going to go, and then eventually the red, depending on how big of a drift that you have. And then, the other thing that can happen is sometimes you'll get the actual color shift if you're not updating your LEDs very often and the dip got so low, during the portions of time where the data wasn't stable, then you might get like a completely different color change or go off or something like that as well. So there's one other topic that I figured was a little bit too advanced for in here, but I'm just going to tell you what it is just as in a general rule. do not take LEDs and low power lines and high power lines and put them together. There's a thing known as inductive coupling. So if you have long runs of wire going along with like LED runs right alongside all your coil wires, when that coil is flipping, you will actually get a transfer of energy from those wires into your delicate LED wiring. Now, what's really bad about this, it's not just the dip we were looking at when the power or ground rose a little bit and the power went out. This is energy coupled in that might be a lot higher, especially on the digital signal. So if that voltage gets above the thresholds of what the LED chips can do, now all of a sudden your LEDs are just burnt out. It's game over for them. So anyway, it's okay to cross wires at 90 degrees. So if you need to go across your high voltage lines and all that, but if you're running the same, wires in the same runs, low voltage and high voltage, you're most likely going to end up with some problems. So anyway, I think that's it for me. Yeah, please come by the booth. If you have any questions, anyone has questions now, I'd love to hear them. And yeah, please check out our website. And we're here for the community. We just love to see all these games come to life, and just love going to all the shows to see all this and talking with the developers. And I'm sure they would be more than willing to talk to you as well. So anyway, any questions? Yeah, go ahead. I think you're supposed to step up to the.
Added extra power and ground to supply all the LEDs. Is there a reason you don't cut out the loop from at the end of the first 5 so that it looks like you've created an artificial ground loop? Is there a reason you leave that connected?
Sorry? Oh, yes. That one right there. Yeah, so it is a good point. The digital lines, so you could get such an imbalance. So it's not so much a ground loop because these are both coming from the same source. But if you get to the point, there is a data line that goes between each one of the LEDs. So if you get to the point where the threshold of what is a logic 1 and a logic 0 between those 2 points, it's like, yes, you could have a problem. But typically, the amount that we're talking, we're only talking a 0.6 volt drop as it was already. So as soon as that other line comes in and doesn't get there, 0.6 is not the threshold at which a logic 1 becomes a logic 1. So we've never seen any problem at all like that. But it's a good point, though.
All right, so when we were talking about separating the toxic ground from the low voltage ground, and you mentioned that the proper way to do that is back at the filter board, I had a quick question on how to properly implement that. So a lot of people have terminal blocks coming out of their grounds because there's only two wires coming out of the terminal, the power filter board. Would you need 2 separate terminal blocks, one for the high voltage toxic ground, one for the regular ground, or is both of those wires going directly to the ground terminal block the same thing? Like, are those 2 pins connected on the board, or are they separate?
Good question. So it depends on what filter board you have. When we start getting into commercial machines, we actually redid the filter board and we added a lot more connections. So if you use the modern filter board, we call it the smart filter board, and then use the cabinet interchange board, which is simply just a connector that goes at the very bottom of the playfield, because we only need power and 2 RJ45s for the most part to run everything. So you pull off the power connector, pull that off. Well, there's a whole bunch more ground ties in there, and that board still keeps the toxic ground away from all the other delicate ground. So yeah, I'd stop by the booth and
whichever one you were selling 4 years ago when I built my game.
Yeah, so it probably changed about 2 years ago and things. So yeah, so look for the smart filter board and then the interconnect board, and it takes care of all that for you.
Thank you for this. This was awesome.
Yeah, thanks.
Yeah, thank you. This was really great. Really appreciate it. It was very informative. Learned a lot. And I was wondering if this is on your website, this PowerPoint, or if it's possible to get a copy of it.
Boy, I just created it for the show, but yes, I will definitely make sure it's up there. I'd like to probably add a lot more because there's a lot of bullet points I said that weren't on here. I didn't know if I could get through. There's 50 slides in here, but yes, I will definitely put it up there.
It's a great slideshow. Love it.
Well, thank you.
Thank you.
Yeah. All right, is there any other questions? All right, well, thank you so much. And yes, please come by the booth. We love to talk about this stuff. And yeah, if you have any more pressing questions, you don't want to do it here, please come by and talk to us. Thank you.
Again, many thanks to Dave Beecher from Fast Pinball.